Hello students, welcome to Sri Jayendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 7 of our unit Mechanical Properties of Fluids. So let's begin with today's class. This is the introductory session of the surface tension. So let's first discuss what surface tension is. Let's have a look. Let's suppose look at the diagram that you will see that some insects like we can say a water spiders walk on the water surface as if they are walking on a straight elastic membrane, and their feet produces dimples on the surface film without rupturing the films. As you can see even from that water droplets are leaving the water tap, that even it is creating a certain surfaces. That how this is possible, let me show you one more example. The bristles of a paintbrush spreads out when the brush is immersed in the water. However, when the brush is taken out, the bristles cling together. As you can see, this is the situation when it has been taken out. So why this happens and what is the principal phenomena behind this? So to understand the phenomenon of the surface tension, let us understand the following terms first. That we need to understand a cohesive force, adhesive forces, range of attraction, sphere of influence, free surfaces, and surface film. So let's understand one by one what cohesive force is. Let's suppose assume that this is one of the container, and in this container we have filled a certain water in it. So what we understand is, let's understand this is the one molecule of a water, this is the another molecule of a water, and between these two molecules of water there is a certain force of attraction do exist. And this force of attraction, what we call as the cohesive force, this is the force which is acting between similar particles. When I say similar particles, I mean it's between the water, or let's say wood, or let's say suppose glass, and something like that. So when these two elements are having a force of attractions, they is known as the cohesive force. Now let's look at this molecule and this glass surface, or let's suppose consider this surfaces. Let me show you. Yes, this surface is that all the particles or all the molecules, they are residing on the boundary of it. That between this water molecule and between, let's suppose this is a glass beaker, then glass beaker having certain kind of forces. So this is what we call as an adhesive force. So this force does exist between the different particles. So when it is the force, let's suppose wood, and let's suppose the glass and mercury, let's suppose the glass and water, let's suppose the wood and steel, all these forces can be considered as an adhesive. So if you have seen the advertisement of the Fevicol, I hope you have seen it. Yes, it has been said as an adhesive. That's why it has been called as an adhesive, because it is going to stick to different elements. As it is going to stick to different elements, that is why we call this as an adhesive one. I hope this is clear. So I hope two forces or two situation, a cohesive force and adhesive force, these two words are clear to you. Is it clear? Is it clear? Great. Now, now let's suppose understand that these two molecules will attract each other if and only if they are separated at a distance which is equals to less than or equals to 10 to the power minus of 9 meter. And this first molecule and second molecule, they are going to attract because of their force of cohesion. This force is known as the range of attraction, which is very less. So molecules having distance which is greater than the 10 to the power minus 9 meter, all the molecules which is having the force or which is having the distance greater than 10 to the power minus 9 meter will not attract each other due to force of cohesion. I hope this is clear. Is it clear? Is it? Now, let's look at what we have done is that this is one of the molecule, and for this we have create one imaginary sphere with the range of attraction as the radius around this molecule, and this sphere is known as the sphere of influence. So all the molecules which are in the sphere of influence exert a force of attraction on the molecules which is at the center. That means let's suppose a certain molecules are lying in the sphere, then this all will be having a force of attraction due to this molecule. But let's suppose certain molecules are residing over here, then all these molecules, let give me the number, it's a 1 2 3 4, this all four molecules are residing outside the force of attraction range of the sphere, and when they are residing outside, they are not going to be attracted because of this molecule. I hope this is clear. Is it clear? So this is sphere of influence. Within this range, a force of attraction does exist. I hope this is clear. Is it clear? Is it? Great. Now let's look at this again. This is the container. This is the container, and we have filled this container with water. So if you see the upper layer, if you see this upper layer of the water, this will behave as a stretch membrane. But this topmost layer, this layer that resides on the top of that, it's a topmost layer of the liquid, is called as the free surface. And the layer of surfaces of liquid, the layer of surface of liquid whose thickness is about equal to range of the molecular attraction, that is what we call as a surface fill. I hope this is clear. This is surface fill. Is it clear? So first cohesive force, second adhesive force, next force of attraction, next range of attraction, next it would be the sphere of influence, and next it's a free surface. Everything is clear. Is it clear? Is it? Do you have any doubts up till now regarding this all? Is there anything? Is there? No? Great. So now let's look at certain quick questions. It says that it's an attraction between two water molecules. It's an attraction between two water molecules. It's an adhesive force? No. Between two water molecules. No effect on water. No. It's a cohesive force. Yes, this one would be the correct answer. Next, a range of attraction. It's a 10 to the power minus of 9 meter. Range of attraction would be a 10 to the power minus 9 meter. Next, if a molecule comes in the sphere of influence of other molecule, then it is going to be attracted because this force will be attractive in nature. I hope this is clear. Does it clear? Does it? Do you have any doubts up till now? Anything? Anything? No? Great. So now let's discuss the surface tension on the basis of the molecular theory. Let's have a look. Let's understand this situation. We have three molecules. One molecule A, another molecule is B, and another molecule is the C. So if you look at this molecule A, then let's suppose this is the center of the molecule, and this is going to be attracted from every molecule. Let's look at this. I hope this is clear to you that it is going to be attracted due to this all the molecules that are within the sphere of the influence of this sphere. So that's why if I understand and if I talk about the net force acting on this, that would be equals to 0 because everyone is attracting it, and this total amount of force that is acting is 0. Now let's talk about the second molecule. It's a molecule B. So when I say molecule B, this is going to be attracted like this is going to be attracted like this is attracted like this is attracted like this, and everything. But as there is a certain section which is filled with the air because it is the outside the liquid, so on the upward direction there is certain little force would be the less, And as this little force would be the less, this is going to have a net force on the downward direction. So I could not say it's a net force is 0 because a net force is acting over here. Now let's discuss the situation. Let's discuss the situation of particle C. That if you see this, it is half within the water and approximately half it's outside the water. So when this would be the situation, it is half would be outside the situation. It is like this. I hope this is clear. Yes, it is going to be attracted in the downward direction. But what about the situation in the upward direction? No one is attracting it. Why? Because no layer is there. So it is having net force. It is having net force in the downward direction. So the situation is what you understand and what things must be clear is that let's suppose this is the liquid, and as this is the liquid, this upper layer, I'm talking about this layers only, this layer is having a certain kind of force of stretching and which does acts in the downward direction. That's why it look like this. This will behave as a stretch membrane. It's a just free surface. This free surface or the top of the layer or the upper layer will behave as a free surface, and this is having a force. How this force occurs, let's understand the situation of C and you will feel it. I hope this is clear. So this tension is what we call as the surface tension. I hope this is clear. Is it? Let's have a quick questions. It's the free surfaces of the liquid film behaves as, yes, it's a stretch elastic membrane. This would be the correct answer. Next, surface tension is a blank phenomenon. It's a surface phenomenon. Yes, that do exist. That does exist on the surface, or I should say on the free surface of a fluid. Now let's take the definition of surface tension and its examples in the practical or day-to-day life. So surface tension is defined as the, it's a force per unit length acting at right angles to an imaginary line drawn on the free surface of the liquid. So first thing, it's a force directly proportional to the L, and if it is directly proportional to the L, then if I replace this proportionality symbol, I can have one constant, and that constant can be represented as T, and this is T, which is surface tension. So this T would be given as, which is equals to F by L. It's a force per unit length. I hope this is clear. So this is line AB, and if you imagine a certain string or line over here, then this is going to be attracted by this forces, and this force is on this side and this force is on this side. I hope this is clear. So surface exerts a force which is tangent to the surface, and this surfaces exert a force which is perpendicular to the imaginary line. You can see this, that this all forces are perpendicular. I hope this is clear. So this is what surface tension is. Now now it's a, let's suppose define it. It's a surface force. It's a F, as we have discussed. It's a F is equals to T into L, and from this it's a T is equals to F by L. This is what we call as a surface tension. Its unit, it's a Newton per meter. This is surface tension. So if F is the force that is acting on the imaginary line of length L, then surface tension T could be written as T is equals to F by L. I hope this is clear. Is it clear? Do you understand any query up till now? Is there anything? No? Great. So let's consider one of the needle on a water surface. This is the needle and this is the water surface. So as this needle is going to be applied by the force, and this force does exist by these water molecules, this water molecules will apply a force in a perpendicular direction from both the sides. As you can see, this is what surface tension is all about. I hope this is clear. Is it clear? Let's take the one more case, that let's suppose consider one of the ring in the water. And when we have one of the ring in the water, a surface film, a surface film is formed in the ring. And when surface film is formed in the ring, then the this water molecules will apply a force, as you can see this from the outside, all these forces, as well as from the inside. So forces are acting on both the sides, from outside as well as from inside. And the total length at which surface force is acting as shown in the figure, as you can see this. So this is the situation. This all are the practical situations of the surface tension as you have seen it. Yes. So now, are you clear with the surface tension, what it is and how it behaves? Do you? Great. So surface force is blank to the surface. Perpendicular? No. It's a tangential? Yes. It's a tangential force to the surface. It's a surface force. Next question. It's surface force is perpendicular to the object. Yes. Repeated question. I hope this is clear. Is it clear? Now, it's a behavior. It's a behavior of surfaces under the surface tension. Let's have a look. Let's suppose there are two soap films in this ring, and this was the ring that is having two soap surfaces. This is first, this is second. So let's suppose consider a thread which is tied to the ring, having the length which is slightly greater than the diameter of the ring. And if this has having a slightly greater diameter than the ring, then there is a formation of soap film inside the ring. If we dip the system in a soap solution, that I'm sure you must have done it, that if let's suppose a circular ring is there, and deep that ring into the soap solution, and a certain film kind of thing has been formed, and on this free surface of this soap film there is a surface tension. So the net force acting on the wire on is zero, because all the forces, whatever positive force is acting over here, that is acting over here too. So this is positive, this is negative, this is positive, this is negative, this is positive, this is negative, and onwards. I hope this is clear. Is it? Is it clear? So we have now seen only the practical aspects and practical situations of the surface tension. Are you clear with this? Are you? Now let's discuss in a detail with the surface energy, what it is. So what we can say is that all the molecules in the surface film possesses a greater potential energy than those inside the liquid, and the surface film as a whole possesses a certain amount of potential energy, that is what we call as the surface energy. So if I want a definition of surface energy, it is those potential energy per unit area of the liquid surface film under isothermal condition. Yes, temperature remains the constant, is called as the surface energy. So surface energy, its a potential, could be written as it's a surface energy, that could be given as surface tension multiplied by change in the area. Yes, this is the formula. This is the formula for the surface energy. I hope this is clear. Let's look at certain quick questions. Unit of surface tension. Yes, it would be a joule per meter square, and if it is a joule per meter square, it could be arcs per centimeter square too. It's both A and B. This would be the correct answer. Let's look at the next question. It's a molecules. Molecules in the surface film have blank potential energy than molecules in the bulk. Yes, so molecules in the surface film having a more potential energy than the molecules in the bulk is having. Is it clear? Great. Now let's define the relation between the surface energy and surface tension. Let's look at this very carefully. That we have one rectangular frame, as you can see this, it's an A, B, C, D, and this rectangular frame is having one of the slider. So this slider can move in this direction, or this slider can move on this direction. That depends on the situation. So what we have done is we have dipped this rectangular frame into, let's suppose, the soap solution. And when I have removed this film, when I have removed this, as you can see, this rectangle is having a soap film attached with it. So the wire, when this soap film is attached with it, let's let's understand that what are the forces that is acting, what are the forces that is acting on the system, that all those particles, look at this, all particles, as you can see, this all particles are on the boundary of this liquid film or liquid solution. And if this film is on the boundary or liquid solution, then this is going to be attracted inside it, because it is always the force of attraction. Now let's suppose if you wish that this slider should not move in that direction, what you need to do is you need to apply certain force in this direction. So effect of this force can be nullified. So let F dash is the force that is being applied on the wire, and that force is being taken to overcome the surface force, that is what we are talking about. And to make some displacement, that means if I apply a force, I want that there should be certain displacement in the wire too. And when I'm going to shift this wire, it is basically I will change the area of this surface fill. I hope this is clear. So let's look at the next situation. Initially this slider was over here, as you can understand it. It was just the filled with the A, B, C, D, and I have applied certain force. As I have applied certain force, this area has been changed and this area is increased. So as this is being changed by the dx length, I understand that surface tension, it's a force applied divided by length. And from this force applied would be equals to surface tension into length. So from this we understand that work done would be equals to force multiplied by displacement. And if it was the work done is equals to F dash into dx. So this force could be written as T into L into dx, and this work done is equals to twice of T into L into dx. Now the surprise is that why this 2 is there, because as it was the soap solution, there are two free surfaces, one on the upper side, one on the upper side of the soap film, and one at the lower side of the soap film. So when they used to say that it's a soap film or it's a soap solution, you must be clear in your mind. You must be clear in your mind that it will be having a two free surfaces. I hope this is clear. Is it clear? Is it? So it is 2 into T into L into dx. Always remember this. Now let's suppose this L into dx is the change in area. So this is equals to T into dA, and it is the situation where dw by dA is equals to T. So this work done will store in a form of the potential energy divided by area into T. Or I should say this that potential energy, or this is what we call as the surface energy, is equals to number of free surface multiplied by surface tension into delta A. I hope this is clear. This n will represent it's a number of free surfaces. T represents the surface tension. T represents the surface tension. And this delta A represents it's a change in area. So this potential energy or this surface energy would be equals to n into this energy, or the work done, or the surface energy is n into T into delta. Always remember this. Yes, I hope this is clear. If surface tension is equals to 1, if if change in area is equals to 1, then surface energy would be equals to surface tension. But this is just the numerical value. I hope this is clear. Is it clear? So have you noted this? Have you noted this? Do you understand this? Yes. Now, do you have any question? Do you? Do you have any question up till now? Is there anything? Is there anything? No? Great. So now, are you ready for the questions? Let's work on with the questions. Find out. Work done. Require to blow a soap bubble having radius r. You need to blow a soap bubble having radius r. How will you do this? So what I understand is this work done is equals to n multiplied by t into delta A. When they say you need to blow this, that means initially they does not have any existence of the slope bubble. So what you need to do is you need to develop it from a zero radius to, let's suppose, an radius r. I hope this is clear. Is it clear? Is it clear? Great. So it's a then they said it's a soap bubble, so n would be 2. Let's call surface tension T only. It's a 4 pi r square minus of 0. So this is equals to T multiplied by 4 pi r square multiplied by 2. It's an 8 pi r square. This is the work done required in joule. I hope this is clear. Is it clear? So it's a work done equals to T multiplied by 8 pi r square in joule. This amount of work done is required to blow a soap bubble having the radius r. I hope this is clear. Is it clear? Is it? Great. Now let's work for the next question. That the length of a needle, the length of a needle floating on water is 2.5 centimeter. Calculate the added force required. Calculate the added force required to to pull the needle out of the water. So the surface tension required is equals to, it's a 7.2 into 10 to the power minus of 2 Newton per meter. This is the surface tension that is required. How will you do this? How will you do this? It is basically a needle, so you can assume this is something like this. And if it is a needle, that means it must be having the two free surfaces, one of the free surface over here and one of the free surfaces over here. So it is F directly proportional to the L, or you can say it's a F is equals to N into T into L. So you want this force required, so this is equals to, as it is having the two free surfaces, this is equals to 2 into T into L. This amount of force is required. So this is F is equals to 2 multiplied by surface tension, which is equals to 7.2 multiplied by 10 to the power minus of 2 multiplied by length, and this length, it's the 2.5 centimeter, so it's a 2.5 divided by 100. I hope this is clear. So if I solve this, it is just the 3.6 into 10 to the power minus of 3 Newton. This amount of force is required. This amount of force is required to pull this liquid, to pull this needle out of the water. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's work for the next question. Suppose the question says that a paper disc of radius r, from which from which a hole of radius r, a hole of radius r is cut out, is is floating on liquid of surface tension T. The force on the disk, the force on the disk due to surface tension will be. How will you do this? So a paper disc is there. It is having the radius r, from which a hole of radius r is cut out, and which is floating in a liquid of surface tension T. So the situation would be something like this, that this was the paper plate, this is the center, it's having radius r, and from this a hole has been cut out. This is a small r at small r, and this inner section has been cut out and it has been separated. Now the force on the disk due to the surface tension is required. So what we can do is, it's a surface tension that is equals to force applied divided by unit length. When I say length, what I understand is I always take for the 2 pi r plus even this length, it's a 2 pi r. So this is equals to, this is f divided by 2 pi into r plus r. And from this as they asked about the forces, it's a force which is equals to 2 pi t multiplied by r plus r Newton. I hope this is clear. Was it clear? Was it? Are you sure? Are you sure? Great. Now let's work for the next questions. Let's suppose they said that find out the work done required to change the radius of soap bubble from 10 centimeter to 20 centimeter. They have said that surface tension of soap solution surface tension of soap solution is 25 into 10 to the power minus of 3 Newton per meter. How will you do this? What could be done? So what I understand is, it is basically the work done, which is equals to number of free surfaces multiplied by T multiplied by change in area. So as they have required, it's a soap solution, number of free surfaces would be 2. This is surface tension T multiplied by 4 pi, it's r final square minus 4 pi r initial square. So this is equals to 2 into 4 pi, it's an 8 pi T multiplied by r final square minus r initial square. So this is equals to, let's put up the value and get it done. This work done, it's an 8 multiplied by pi multiplied by surface tension. This is equals to 25 into 10 to the power minus of 3 multiplied by this is our final square. This is 20 square multiplied by 10 to the power minus of 4 minus of, it's a 10 centimeter square, it's a 10 square into 10 to the power minus of 4. So if I solve this, what I get is it is equals to 0.24. It is equals to the, this will be the work done in certain joules, in certain joules. I hope this is clear. You can solve this easily. Have you? Do you have any doubts up till now? Is there anything? Is there anything? Are you sure? Are you sure? Great. Now let's work for the another questions. This surface energy and the surface tension can form a many other questions, and this has been asked. If you go through the previous questions of the examinations, you will find many questions based on this concept, because this is the concept which requires certain logical aspect. That's why this is having a very high probability to be asked. Let's have a look. Let's suppose they said that if a bigger bubble if a bigger bubble of radius r splits into n smaller identical bubbles identical bubbles, find out work done required. So what I want the work done to be done, and that is to be calculated. How will I do this? So what I understand is that, again, that a bigger bubble is there and it is having the radius r, and this is going to be divided into n smaller bubbles. So first thing is I need to have a relation between these two radiuses. So it is just the 4 by 3 pi r cube, that is equals to n times of smaller bubble, which is equals to 4 by 3 pi r cube. And from this it's a 4 by 3 pi, 4 by 3 pi could be gone, and this is equals to r cube, it is equals to n into r cube. So it's an r which is equals to n to the power 1/3 multiplied by small r. I hope this is clear. From this that could be, this could be given as, this is equals to r square, which is equals to n to the power 2/3 into r square. So if we require this, we will solve this. I hope this is clear. So from this that could be, work done could be calculated as, it is equals to n to t into delta a. Let's consider n equals to 1. So this is just the work done equals to t into delta a. So if it is like this, it's a work done which is equals to surface tension multiplied by change in area. This is equals to t multiplied by delta a. So initially it was a single bigger bubble, and finally it is having a n smaller identical bubbles. That means your area would be n times of smaller bubbles area. It's a n into 4 pi r square minus initial, it is a 4 pi r square. Now let's just replace this radius with any one of the radius. Though we have this relation, it's an r square is equals to n to the power 2/3 into r square. So this could be given as, it's a t multiplied by n into 4 pi r square minus of 4 pi. Capital R square could be written as n to the power 2/3 into r square. So this is equals to t, multiplied by this 4 pi r square, this 4 pi r square, this is 4 pi r square, this is t into 4 pi r square into bracket n minus n to the power 2 third. This will remain. If you want, even you can remove this n as well. I hope this is clear. Or even this can be done, that this r square has been replaced by the capital R. So that depends on your understanding purpose, or your your choice, that I will change this radius or I will change this radius, or that depends on the data given as well, that the smaller radius is given or capital radius is given. You can change it accordingly. But is it clear? Is it clear? Are you sure? Are you? Great. So this is the work done required. Now let me extend this question, that let's suppose this, the situation is, does the surface energy increases or decreases? Yes, it is just the in continuation with the previous question, that when we have this, break this bubble into n number of small identical bubbles, does this energy has been increased or does this energy has been decreased? What has happened? So as I can understood is that if I calculate this 4 pi r square, and if I calculate this n into 4 pi r square, this is the area initial, this is the area final, and as I understand, area final is greater than area initial. So it was the work done, that is equals to surface energy, that is equals to T into delta A, and the delta A was the A final minus A initial. So as A final is greater than A initial, the final surface area is greater than the initial surface area. This work done, this work done, or I should say a surface energy, I should say it's a increases. I hope this is clear. So this work done or this surface energy increases because this work done is positive. I hope this is clear. Now, if what I say it is that if this surface energy has been increased, who have given this energy? Who have given this energy? And if someone has given the energy, what is impact? What is impact on that energy? So let's understood that suppose atmosphere has provided, let's suppose atmosphere has provided their energy to break this bubble, to break the bubble. So it might possible, so it might possible that temperature temperature of atmosphere, the temperature of atmosphere decreases, and this decrease in temperature can be calculated as q is equals to m into s into delta theta. As you are aware with the every numbers in this is what you have used in the thermal properties of matters too. So this could be calculated easily by m into s into delta theta, that is equals to work done or that is equals to surface energy. I hope this is clear. Now let's suppose understood that if we merge n identical bubbles to form to form one larger bubble. Find out and discuss every previous situations. How will I do this? So this is completely reverse process. In first process, what we have done is that we have divided, we have one single bubble, and from that one single bubble we have splitted it into the n identical bubbles. Now we are doing the exactly reverse thing, that now we are having the n identical bubbles, and from this n identical bubbles I am going to form a one larger bubble. So in this situation it is something like this, that we are having n multiplied by 4 by 3 pi r cube, that is equals to capital 4 by 3 pi r cube. And from this I can remove this, it's a 4 by 3 pi, 4 by 3 pi has been gone. So this is equals to n multiplied by r cube, this is equals to r cube. From this it's a n to the power 1/3 multiplied by r, this is equals to capital R. So this is situation that n to the power 1/3 multiplied by small r would be equals to the capital R. From this it's a work done, which is equals to T into delta A, which is equals to, it's a surface tension multiplied by 4 pi. Now finally it is going to be a one bubble, it's a 4 pi r square minus n into 4 pi r square. So it's an n to the power 2/3 into r square is equals to capital R square. This is equals to T multiplied by 4 pi n to the power 2/3 into r square minus n into 4 pi r square. So this is equals to T multiplied by 4 pi r square into bracket n to the power 2/3 minus of n. I hope this is clear. This is the work done. Is it clear? Have you got this? Have you got this? Are you sure? Do you understand this? Do you? Are you serious? Are you? Do you understand this completely? Great. So this is the work done. Now let's discuss about their energies. As we have merged n identical smaller bubble to one big bubble, its surface energy will decrease. So surface energy, or I should say work done, will decrease. And if this will decrease, so this loss of energy can be gained by whom? By whom? Yes, energy, this energy can be used by an environment. It's an environment to increase the temperature, and this increase in temperature could be given as Q is equals to mc delta T. This increase in temperature can be calculated as, it's an m into c into delta T. I hope this is clear. Would it be clear? Would it be? Are you sure? Do you have any doubts up till now? Is there anything? Is there? No? Great. So can you do this kind of questions? Can you do this kind of questions? Are you sure? Do you have any doubts up till now? Is there anything? Is there? No? Great. So now let's wind up this session over here. This was all about the surface tension and the surface energies. Please go through this session very carefully, as this is a topic which is having a very high probability to ask. Please go through this, revise it, and do as many questions as possible. Thank you. Have a good day. Take care. Bye bye.